Okay, thank you, Robert. So after the lecture yesterday, somebody asked me if there was a reference they could read about this stuff. And for this, I would recommend the book that Sean mentioned in the first talk yesterday, Quantum Riemannian Geometry, Chapter 1. It has a very good introduction to everything that I said. And now let us start by finishing the material on exterior algebras, which we didn't get time for yesterday. So yesterday we defined first order calculi, and an exterior algebra is sometimes also called a differential calculi, just without the first order qualifier. So over an algebra A is a differential graded algebra with a product, which I will annotate by wedge, although you should not think that it's a skew symmetric in the classical sense product. It's just some algebra product now. And a differential such that wedge is a graded product and degree D is a graded map of degree 1. D square is equal to 0, of course, it's a differential. And it satisfies a graded Leibniz rule with respect to the product wedge. So this formula should be understood in terms of pure elements of pure gradation. So let's say that the grade of A is A with this notation. And most importantly, we should have a surjectivity condition, which means that this algebra is graded either with the wedge and D by order 0 and 1, or either by the wedge from order 0 and 1, or by wedge and the D from order 0. And lastly, to say that it's over the algebra A, I mean, this is just an abstract exterior algebras at the moment, no mention of A, but to be over A, the zero graded component should be A itself. And the wedge in degree 0 would just be the algebra product of A. Right, so I have one remark about this. Here we write the wedge product as a k-bilinear map. But actually saying that this is an associative algebra forces this product to descend immediately to the A tensor product between these two, because we can write F is now an algebra element, so degree 0. And theta and eta are higher degree forms. And now simply move the bracket. So in fact, wedge descends to a map. Omega kd tensor over A. Omega p d to degree k plus b. Okay, so now let's define one more thing, the tensor algebra. So this is if we have a first order calculus again. And you notice that I'm using the same notation for first order calculi as the first gradation in the exterior algebra. That's of course not a coincidence. Let's talk about that in a moment. So we define the tensor algebra as a k-fold tensor product of the omega 1d over A. Okay, so like I just mentioned, if you take an exterior algebra and you forget everything about the first order, first degree part, then you get the first order calculus. That's very simple. And it just follows immediately from the Leibniz rule, the graded version. But on the other hand, and a bit less trivially, given a first order calculus, we can make the so-called maximal prolongation and extend it in a universal way to a exterior algebra. And I think people already mentioned this yesterday, but okay, let's discuss it a bit further. there exists a maximal prolongation. And this prolongation, sorry, I need to find a bigger piece of chalk. This maximal prolongation is universal amongst exterior algebras giving the same first order. So it's universal amongst exterior algebras restricting to the same first order calculus. And this is given by taking the tensor algebra, which we just defined, and quotienting it out by a certain differential ideal. And this ideal is the minimal one that we can take in order to have the graded Leibniz rule be well defined. And we can also describe this ideal explicitly. It's generated by taking the space of first order differential relations, which I call MD. And applying D to it in a certain way. And so it just looks like taking elements of the first order differential relations, and instead of having A and B, you take dA and dB. It doesn't look terribly nice, but it's what you get. So proof. Well, first of all, the tensor algebra is a universal object for associative algebras, which are bilinear in the product operation. So the surjection from the tensor algebra is clear. And then all you have to do is describe the differential ideal, which is the kernel of this. And to do that, we should have d of 0 be equal to 0. This will be d of the class of 0, which will be d of which will, if you use the Leibniz rule, be precisely d of things that come from nd. And then you use the graded Leibniz rule on this, and you apply bracket operation, and you will simply get this kind of thing. And this guy was really zero before. So we needed it to be zero as well, otherwise everything will be poorly defined. So we take the pre-image of this wedge product in the tensor algebra, and that will be the tensor product which appeared here. So that's the first part, and it gives you the generator. Now you should also check that no further relations are necessary, but I think we omit that in the interest of time. It's not very long computation or anything, but still. Now, the obvious example that you can do is take the differential calculus that you always have, the universal one, and you ask, what's the maximal prolongation? Well, by this description, the ideal is generated by the image of something in nd, and nd for the universal is just zero, so the ideal will be zero as well. So actually, maximal prolongation is just going to be the tensor algebra for universal. Okay. That was what I wanted to say about exterior algebras. Now let's talk about something completely different, which is some classical differential geometry. So this will mostly have the character of motivation for why you would want to try to consider differential calculi in the first place. But it turns out that the exterior derivative is actually very important. I mean, we all know it's important, but it's actually even more important than you might expect intuitively. Bob told us yesterday that in the beginning, God created the complex semi-simple Lie algebras, or even the complex simple Lie algebras. But actually, I'm going to provide some evidence that in the beginning, God created the exterior derivative. So we'll have some theological arguments. So this is going to be done by considering a functorial description of what it means for things to be geometric and what constructions in differential geometry actually are. And to do that, we're going to start by describing what the geometric object is. If you want a reference for this part of the lecture, it can be found in the book Natural Operations in Differential Geometry, specifically sections 12, 14, and 19. One of the authors is here, Jan Slovak, I think. So a natural bundle is a kind of functor on the category of manifolds. And for the moment, let's think of manifolds of fixed dimension. And it should take values in fibered manifolds of some dimension. And then we should have some naturality properties in addition to just being a functor. So first, in this category, you have a natural projection map. This projection should give you a natural transformation which reproduces the base as the origin of this. So the projection pi f is a natural transformation from f to the identity functor on manifolds. And let's say dimension m. So that basically means that you get a fibered manifold over the same manifold that you started with. Secondly, you should have a localization axiom. So how it behaves with respect to embeddings of open subsets. So if phi from U to M is open, or the embedding on open submanifold, I should say, then the image of the functor is just an inclusion of an open subset into the total space of the target. And sorry, I realize now that I have two notations that are too similar. This is supposed to be the category of filtered manifolds, and this is fibered manifolds, and this is supposed to be a curly f. And this is just the value of f under the manifold M. I hope that's okay. And finally, one more property. If you have a smoothly parametrized family of morphisms, then it gets pushed through the functor to a smoothly parametrized family of morphisms. Okay, now the setting of natural bundles in this sense is general enough that it encompasses every geometric construction that I've ever heard of. If you combine it with some extra things like taking global sections, other natural and obvious constructions. So let's talk about some specific cases of these guys, more specifically jet bundles and jet constructions. So we're going to start by defining what it means to say that two curves have contact of order k, or their k equivalent. So here's our symbol for our relationship. It's pronounced gamma and delta have contact of order k, or kth order contact. Sorry? I have not written how it's defined yet. Yes. So kth order contact, if for all functions, smooth functions even, so we're pulling back our function by gamma and delta to produce functions from R to R. And then we're differentiating them. This should vanish for all derivatives up to k. Okay, and once you've made this definition, you can get a fairly powerful lemma with very little work. So this is not the lemma, this is the lemma for the lemma, but it's also necessary. So let's take a smooth map. If you have kth order contact, then the pullback along the smooth map will also have kth order contact. Maybe we just emphasize that it's smooth. And the proof for it is very trivial. If you have a function on n, then the pullback along phi is a function of m. So we can just take this whole thing and use the definition of kth order contact. It's just a matter of thinking about whether you caring about this curve or whether you're caring about this function. Now that we know what the curves with contact of order k are, we can define jets. So we have two maps, phi and psi, from manifolds M to N. We will say that they have the same k-jets at the point x, or which is written like this. J k x phi is equal to j k x. Or you can omit the x and put it like this. And let's write that down again. Phi has the same k-jet as psi. If for all curves gamma with gamma at 0 is equal to, okay, this is maybe too much white. Gamma of 0 is equal to x. Oh, yes, I forgot to say about kth order contact. For order 0, alpha equal to 0, this just means that the curves have the same value at 0. So that's implied by having kth order contact or satisfying this equivalence condition. They both go to x. Yes. Ah, thanks, Mauro. Yes. Yeah, certainly you should talk about what happens at 0 only. It's a local condition. Anyway, we say that these two maps have the same k-jet if for all curves with the same base point, pulling them through phi and psi have kth order contact again. Yes, x is in M. That's right. Okay, and now we get a really useful proposition for very little work, which is what I promised earlier. Unfortunately, it's a bit convoluted to write it down. We need a lot of different maps, some of which have the same jets. But let's use some tildes and try to keep them with the same order. So if you have two maps, phi and phi tilde with the same kth order jet at x, and you have another pair of maps which have the same kth order jet at the value psi phi of x, and maybe we just write let phi of x be equal to y to simplify the notation a bit. So anyway, if the two maps phi and phi tilde have the same jet, and psi tilde have the same k-jet, then their composition also has the same k-jet. Okay, so let's, thank you. We take a curve through, to prove this, let's take a curve through 0. A curve which goes through x at 0. Then by definition, not equal. We can take phi and phi tilde pull back, get the same kth order contact. And then we use the lemma. And we just use now the fixed map psi tilde. And then by using the condition on the jets of psi, we get and then finally, we get what we actually wanted, which is the one with no tildes on the left-hand side and 2 tildes on the right-hand side. Okay, so this is a proposition which we can prove in 2 lines, maybe 1 line if you write really small. But actually, it gives you a lot of structure, much of which could be usefully generalized to non-commutative geometry. So, for instance, you get things like jet groups, because this composition is now associative and doesn't depend on representative. Jet functors, jet categories, jet algebras. So let's just expand on that for a moment. So let's just name the set of all k-jets of maps between 2 manifolds M and M. And then if you happen to have a particular map, you can send it to its jet representative. And this is called the k-jet prolongation. Okay. Yes.
So when you say a good of a map, you mean a good at a
Right. So this space is actually a fiber bundle, and the fiber over the point is all the kjets over that point. So over the point x, it will have the jet at x to order k. And this means that you have this map going from M and into the. So what do we really want from this? Well, this construction is actually a bifunctor. Which goes from the product of manifolds M. We will just fix the dimension for now. Times manifolds of arbitrary dimension. And going into fiber manifolds, as I mentioned just now. And this bifunctor is basically the origin of all the other natural operations. I will not go through it in detail. It's in the book that I mentioned earlier. But every other geometric object can be derived from this one. So some examples. Well, we have two arguments, and we can fix two of them. So for example, let's fix this to be the real line R. And let's take the one jet. So this is possibly the most natural thing I can think of. What is this? Should be something you heard of. Well, of course it is. This is the tangent bundle. So now we can switch this around. And make another functor. What do you expect this to be? I'm sorry to say, it's not the cotangent bundle. In fact, the first jet bundle, which this is called, is just its own thing. But the cotangent bundle is a subfunctor of this one. And it just embeds in there in a natural way. So you can derive the cotangent bundle from this. It seems that I'm getting short on time, so I will state the results that I wanted to get to, but I will omit the proof that I was planning. The first one is the Peter theorem from the 60s. It's rather famous. Let L1 and L2 be vector bundles over M. And let's take an operator between their sections. Which is support non-increasing. So that's another way to state that it's a local operator. Then if you take a compact set in M, there is some order such that the jets of two sections coinciding means that their difference goes to 0 under this map. So for all x in this K, and two sections S1 and S2, implies that the value of this operator coincides. For all sections. Okay, so this means that locally, every natural operation is going to be a differential operator of some finite order. And if you are working on a compact manifold, then all natural operators will be differential operators. And then there's the question of I forgot one assumption there. We should say that this is linear. That's the original version of the P3 theorem. There's also a nonlinear version, so this assumption is not essential, but this version from 1960 has it. The other one is due to Jan Slovak in 1987, actually, which removes the linearity assumption. Okay, the other theorem. Sorry? No, linear in the sense of linear differential operators, K-linear or R-linear. So let tau RS be a natural bundle, which is a tensor bundle. With S covariant and R contravariant indices. and let delta be a natural operator from this bundle into some other bundle. Sections, of course. Then we have one of two following cases. Either delta is of order 0, so it's just a C infinity linear map. Or it's a composition P times D times Q, where D is the exterior derivative, and P and Q are order 0. And we can also say something about the number of indices. First of all, it has more covariant than contravariant indices. And secondly, it has less than n-1, or less than or equal to n-1 covariant indices. Yeah, it's the dimension of the manifold now. And this P just goes into the forms. Then you apply the D to go to some higher forms. And then you do another 0-order operation to go to some other natural bundle. And we can also say, something about how many indices that has, but let's just say gamma f like we did there. Okay, so that shows that essentially the only natural differential operator is the exterior derivative. Everything else is just derived from that in some way. And if I have time to write one more line, I'll give an example. So there is this nice operation which maps a connection to its curvature and torsion, right? These are natural operations, and they satisfy what's called the Bianchi identities. And actually, the Bianchi identities is just a consequence of this being derived from the exterior derivative. So in particular, you can prove that the first Bianchi identity for a connection with torsion is true by writing for an arbitrary one form d square equal to x, y, z, arbitrary vector fields, of course. Now R is the curvature and T is the torsion of nabla. And I write plus dot 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 because you have a cyclic sum over x, y, z in there. But okay. Now, obviously, since d squared satisfies equal to 0, this is equal to 0 as well. And since theta is arbitrary, this whole guy has to vanish. And that's the first Bianchi identity. And this is due to someone named Delano. From an article called "Why Should the First Bianchi Identity Be True?" Okay, so I think we stop there. Thanks.
But is there some extensions going to operators between general vector bundles?
Non-natural vector bundles. If you just take two trivial vector bundles, then you could do nearly anything between their fibers, right? So I don't know.
This way, there's a hypothesis of naturality in the bundles and the operator.
Yes, so this should be a natural bundle in the sense that I defined before. A natural tensor bundle in particular. Yes, it's a natural operator, right? Sorry?
It looks like an order one operator.
It is.
Oh, so is there a hypothesis that it's?
No.
You're
No.
saying there are no.
This is a consequence. There are no higher order stuff that's not just.
Thanks again.